afternoon, good evening students. Today we are going to talk about Poynting vector, and in the last class we did talk about Maxwell's equation. Now there has to be certain application of Maxwell's equation that is important to study, and this is exactly what we are going to check today. So we are going to talk about Poynting vector, but before that let's just discuss the Poynting theorem. Whenever we are going to talk about the electric field and magnetic field and their connection, we basically are going to consider the electric and the magnetic field together, as we have also seen in Maxwell's equation. If you consider the Faraday's law, okay, or the Ampere's law, you can see that the electric component and the magnetic component are connected. Now J.H. Poynting in the year 1884, he has actually given this theorem. By that time, electromagnetism was the talk of the town. Everyone was more or less working on those kind of topics. So in a uniform plane wave, if you're basically considering a plane wave at any point, okay, so in general, whenever you're considering a wave, it does have an electric field and a magnetic field which are actually moving in a direction perpendicular to each other. So if this is more or less the electric field, okay, the magnetic field will be more or less in a plane which is perpendicular to each other, right? So the magnetic field will be more or less something like this. So the electric field and the magnetic field will be perpendicular to each other, and both of them, if we actually want to measure at any particular point, we'll see that the electric field and the magnetic field intensity is a measure of the rate of energy flow at any point. So whenever a wave travels, it's definitely going to carry some energy with it, okay, and the rate of the energy flow is actually given by this relation. So what is exactly a Poynting vector? The Poynting vector is actually the cross product of this electric field and the magnetic field, and we take it as denote it with P. So P is equal to E cross H, okay, that's the relation. So if you are asked about the Poynting vector, you should state the theorem, and after that you should write down this mathematical form. In general, we can also say that any particular point, how much is the energy. If we want to measure that, we can actually take the concept of Poynting vector. So the unit is watt per meter square, okay, and watt is the unit of power, but here we are basically saying that how much is the energy transferred from one point to another. So energy of power transformed per unit area, okay. So you're going to take it this way. So that's the Poynting vector, but now we need to just derive that. We're going to use Maxwell's equation to derive the Poynting theorem. So if I just want to write down the part that we are actually going to derive, what we can say is, if we are basically going to take the surface integral of this E cross H is, we know, is the Poynting vector. So whenever I am mentioning E cross H, that means we are going to take the Poynting vector, okay, dot d as bar, okay. So if we take the surface integral, we can actually get it as these two factors on the right hand side, and I'm going to show that what exactly it means and what's its physical significance, okay. We're going to look into that later when we derive it into dv. So this is the volume integral. The first term is the volume integral minus del t, okay, and then integration, and then this is epsilon, this is the permittivity, E square is the electric field, okay, divided by 2, okay, plus mu h divided by 2, okay, mu h square divided by 2 into dv. So this is also the volume integral. So if you look into the consistency of the equation, we know that both are volume integral, so that's fine on this side, and on the other side we have got a surface integral. So we've seen before that we can actually get the surface integral to volume integral, okay, using the theorem. So we are going to use that as well later, okay. So this is what we are actually going to prove, but before that I just like to tell you what are these terms, okay. The first term which we have is called the rate. This is what we have already defined the definition of Poynting vector as, okay. So let me just write it down. This is rate of energy flow, okay. This is rate of energy flow per unit area, So that's the first term. The second term is called power loss. Power loss. So obviously if there is an energy and there is a transfer from one point to another, there will be some kind of loss, and that is called the power loss. Okay, and the third term is called the rate of decrease of stored energy, of stored energy. Okay, so if there is a loss, there will be a negative sign. If there is a decrease of stored energy, there will be again a negative sign. So that how it goes. Okay, so let's try to derive this, and we were going to derive this from Maxwell's equation. Okay, so I'm not going to write down all the Maxwell's equation, but quick recap of what are Maxwell's equation that we actually have it here. Okay, we're basically going to have here these equations. Okay, and in the last class I did tell you. Okay, so this is the equation which you're going to use. First is del cross E is equal to minus del B divided by del T. Okay, and the second equation we are going to use is this. Okay, we are not going to use the magnetic field flux density equation. We are going to use the magnetic field intensity equation. Okay, so please remember we are going to use this. That's why I've given you this equation as well, so that you are not confused. All the forms are more or less possible. Okay, so if I write down Maxwell's equation, let's just concentrate on the derivation right now. Okay, from Maxwell's equation, this is very much mathematical. Okay, you obviously need to mention some sentences, but if you can remember the mathematical steps, you are done for this. Okay, from Maxwell's equation, okay, we are going to take the fourth equation and the third equation. Okay, so let's just write down these two equations now. So the first equation or the fourth equation, we're going to use that, very important, del cross H bar is equal to, as we have seen in the last class, J plus del D divided by del T, right? That was the one equation, and the other equation is let me write it here. Del cross E, which is the Faraday's law, the third law, is equal to minus of del B bar divided by del T. Okay. So let's start marking this equation. Let's say this is my first equation and this is my second equation for this particular derivation. Okay. So what we need on one side is E cross H. So that means I have to operate with E for this. Okay, and for this we are going to do some simple steps. Okay, and you have to have a very clear picture of vectors. So the first thing what we are going to do is take, please remember these derivations step by step. In case you don't remember, you should actually, I suggest you should practice, write it and practice E bar. So we're going to take the dot product with E bar, and we are going to use the vector rule. So if I take the dot product with E bar, I can say it is E bar dot del bar cross H bar, okay, is equal to, on the right hand side it is E bar dot J bar plus E bar dot del D del T. Okay, so we have this. Okay, let's mark this as number 3. Okay, now we do have a vector identity. These identities and all this you should remember. Okay, we're not going to derive that. We have vector identity. So if you're going to talk about the vector identity, that's the first thing. Okay, del bar of E bar cross H bar. So if you are basically taking, if you remember, I did tell you, we talked about divergence curl and all. So you are taking del bar, that means this is the divergence of the E cross H. Okay, if you're taking the cross product of E cross H, and if you take the divergence of that, okay, or we can say that we are taking the divergence of any two vectors, I can actually write it down as the second vector dot product curl of the first vector. Remember it this way, okay, minus first vector dot product curl of the second vector. Okay, so please remember it this way: second vector dot product curl of first vector minus first vector dot product curl of second vector. Okay, it's the other way around. It's not 1 2, it's 2 1. Okay, or I think you can guess the second step. We are going to need this, so I will take it on one side. So we have it here. Okay, so or we can write it down like this: E bar, this is del bar cross H bar. Okay, so I've taken it on this side, so this will be something like this: H bar into del bar cross E bar minus del bar dot E bar cross H bar. So I can take this. Okay, now we can put this relation in 3. Okay, let's say I'll put in 3. So if I replace this in 3, I can say, I can write it like this. So this is E bar dot, sorry, this is E bar dot. So in place of that, I'm going to put this equation. Okay, so let's do it. It's important that you don't miss the vector sign, because we are taking a dot product and cross product, so there has to be vector. Okay, there is a important meaning here: del bar dot E bar cross H bar. Okay, if you just read through it, you might not remember. So again, I'm saying, please practice once or twice, because if your one step is wrong, you are missing out on the important points. E bar dot del D del T. Okay, so we are going to simplify this. So what I'm going to do is, let me take the minus sign common, and I will just readjust this. This is del bar E bar cross H bar minus, okay, we're going to take it minus sign to minus. This will become plus, this will become minus, minus of H bar del bar cross E bar. Okay, we are interested in finding out the surface integral of this. Okay, so we're taking it on one side, and then we have got minus of E bar dot J bar minus E bar dot del D by del T. Okay, now if you compare this with what we need to find, you can see that we have got this term already. Okay, we have this particular term. Okay, let's mark this as number 4. Okay, let's mark this as number 4. Okay, now from 2, okay, we are going to use our second equation. Okay, from 2. Okay, from 2, if we take the dot product with H, okay, let's take the second equation and take the dot product with H. Dot product with H. So we have the second equation, and let's take the dot product with H now. Okay, so if I take the dot product with H, I can say it is H bar dot del bar cross E bar, okay, is equal to minus, let me take it out, H bar dot del B bar del T. Okay, and this is my second term. Okay, and this B actually can be written as mu naught H. If you remember, B can be written as mu H. We have already seen it. So what I'm going to do is, I'm going to slightly modify this, or maybe I can write it down in the same line. I can write it down as equal to minus H, and in place of B, I can write it down as H del H by del T, and B is mu into H. We are not talking about free space here, so I'm not writing down mu naught, I'm just writing down mu. Okay, so this is what we have as the dot product. Okay, now we can see that this is H del cross E. H del cross E is here, so maybe we can put this directly. Okay, therefore we can say 4 implies, it's actually not a very long derivation. You have to just remember the steps, that's important. Okay, dot product, sorry I missed out the dot here, don't miss the dots and the vector signs. E bar cross h bar, okay, minus of this. Okay, so if I just try to readjust this, okay, if I take this minus here, it will become plus. Okay, this is minus, so if I bring it here, it will become plus, and then I will take it on the other side, so I'll have it as minus, right? So I can simply write it down as minus h bar dot del bar cross e bar, okay, minus, we already have the other two terms, e bar dot j bar, this term, minus e bar dot del d del t. Okay, so that's how we are going to design the equation right now, and let me mark this as number 5. Okay, now what we are going to do is we are going to consider the terms, okay, one by one. Okay, so okay, I did mistake, sorry, I did not replace it properly. Just let me just correct this here. Okay, so this is, sorry, this is I'm going to take replace this, right? So if I replace this, I have this as h del cross e. H del cross e is nothing but this term. So sorry, I'll take this mistake here. Minus of h del h divided by del t dot mu. Okay, so this term is important. So once we have done this, okay, let's try to simplify this further. Consider term. I'm going to take one more term here and trying to simplify this. So I will take it as del t of h bar dot h bar. Now both are h, okay, but if you go by the product rule of differentiation, I can take it as h bar del h bar del t plus the second term, which is again h bar, so I can write it down as h bar del h bar del t. So this is nothing but twice of the same term, so twice of h bar dot del h bar del t. Okay, so we can write it down as twice of this. Okay, we can, from this we can also say that this is h dot h. So if the dot product of two vectors are taken, we are basically going to get a scalar, and both these vectors are same, so it will be h h. So I'll just write it down as del h of h square, okay, is equal to 2 times, this is the most important step because that is going to modify my right hand side, h bar dot del h del t. What we require is here is h, okay, del h del t, okay, h bar dot del h del t. Okay, let me just not miss out the vector sign here, this is dot here. So that way we can actually get the term. So that means this term which we have is h bar dot del h del t, okay, twice of this was there, so this would be nothing but half, okay, del t of h square. So this is a very important term that we're going to use. See, this is del t of h square is equal to twice of this, so this term would be nothing but half of del t of h square. So this is what we are going to use. Okay, but we do have e term as well. Okay, so I'm going to say how we are going to use it, but before that let me just write down, this is for the magnetic field. Similarly, for the electric field we are going to have it as e bar dot del e bar del t is equal to, we are going to take half of, okay, the same way you can derive it actually, del t of e square. Okay, just in place of h we are going to take e. Okay, so this is it. Now obviously the next step is to replace these terms. Okay, let's just replace these terms. Okay, let's replace it in equation 5. So replacing in equation 5. So if we replace it in equation 5, let me just rewrite this equation 5. Del bar dot E bar cross H bar is equal to, okay, so my 5 equation was minus h del t into mu. Okay, so in place of del h del t you are going to write it down as minus, okay, mu is there already, so I'll take it mu, and half mu by 2, okay, because there is a half here, and in del h del h del t it is half of del h square del t, del h square. Okay, so that's the first term. Okay, minus e bar dot j bar. E bar dot j bar is the most friendly term, we are not playing around with it, this is exactly what we need. Minus, now you see this is e del d del t. Okay, and if you again remember this relation also we did, d is equal to epsilon e. So in place of d I can write it down as epsilon e. So let me write it down in a similar way. So if I replace it, I'll get the term as epsilon by 2, because E dot del E del T, and I can write it down in this way. Okay, I can if I just look into this term, I can write it down as E bar dot del E del T into epsilon. Right, this is exactly what I can write. So here also I'm doing the same thing, epsilon by 2, and E del E del T is nothing but del T of E square. So A del T of E square. Okay, we're almost done now. Okay, we are going to use the idea of volume integral here. Okay, so next, since we need the volume integral on both sides, so let's just take the volume integral. So taking volume integral. Okay, so if I take it on the right hand side, let me say this is the volume integral, this is del bar dot E bar cross H bar dv is equal to, we were going to combine these two terms. Okay, we can obviously combine these two terms, you can in fact simplify. So let me take this first term here, minus of integration over the volume, this is E bar dot J bar into dv, that's the first term volume, minus, I can see this is mu by 2 epsilon by 2. Okay, so that means there is a half that actually is there. Okay, and there is a del t for both the equations, so we can take this del t outside, whether you take inside or outside the integral, and then we are going to take the volume integral. Now in volume integral we have taken out del t, so we are left out with mu, we are left out with h square, we are left out with 2, so we can write it down as mu h square divided by 2. We have already taken the minus sign out, so I'll have one here which is plus. We have taken the minus sign out as well, so it will be epsilon e square divided by 2. Okay, volume integral of this term. So we have the volume integral on both sides. Okay, now we can use Gauss's divergence theorem. If you recall, okay, that was the first thing that we actually did. Okay, if you recall this Gauss's divergence theorem. So if you basically have a volume integral, divergence, and then you take the volume integral, you can directly take it as a dot product. You can directly take that vector, and you can have the surface integral for that. So you can directly going to use the divergence theorem here. Okay, let me just use the divergence theorem. So this is using divergence theorem. On LHS, right? The surface integral and the volume integral equivalent. So if I take this would be the closed integral of this. We have got del bar dot the vector. Vector is cross product of E cross H, so it is equal to the surface integral of that vector. So this would be d s bar, right, is equal to minus of whatever we have it on the right hand side, E bar dot j bar into dv minus del t integration of v mu h square divided by 2 plus epsilon e square divided by 2 derived. Okay, so although it took some time for me to derive this entire equation, because I was showing you the steps and explaining them at the same time, if you just practice it once or twice you can easily do it. Okay, first you have to start with Maxwell's equation, and then you take the dot product with E for the first equation, and then you take the vector identity, replace it, then take the dot product with H with the second equation, and you will see you are going to get a similar term, and then you can replace it as well. Okay, and then you can simplify it, right, and then you have to remember certain things here, and then use the divergence theorem, and then finally you get the relation. Okay, so this is important. Okay, now this E bar dot J bar is actually called the power loss. Okay, I just want to give you one brief note here, okay, that why this E bar dot J bar is actually called the power loss. E bar dot J bar is power loss, as I mentioned at the beginning. Okay, why this is power loss? So power means you should have a watt and all, okay, the unit. Okay, so in general, if I want to derive the relation for this, I can say E bar dot J bar, and if I just look into the dimensions or the formula, well, a unit of electric field is volt per meter. Okay, volt per meter. Okay, potential applied per unit distance. Okay, into joule. So joule is, sorry, not joule, current density. Sorry, J is nothing but the current density, and current density is nothing but current by area. So this is ampere divided by area. Area unit is meter square. And what is V into I? Okay, if I talk about voltage into current, okay, volt ampere, that means we are going to talk about voltage into current divided by, this is meter into meter square, so this is meter cubed. Okay, this is meter cubed. So this is nothing but the unit of power, this is nothing but volt divided by meter cubed. So meter cubed is nothing but volume. Okay, so that is power per unit volume. Okay, so this is E cross H. So E cross H, if you want to talk about, okay, again you can actually take a similar analysis, and we are going to see that the unit is nothing but E cross H is the unit which is nothing but the Poynting vector, not power, Poynting vector. This is watt per meter square. Okay, so if you look into the unit here, you put watt per meter square, and then there is a surface here, so meter square, and then this surface area also has a meter square. So meter square gets cancelled, I get the dimension is watt. This side it is E dot J, so E dot J, it is volt per volume, so volt per meter cubed. So again I can actually get it, sorry, not volt, very sorry, it's not volt, it's power, right? V into I is power, so it is watt, right? So this is V into I is power, so this is watt by meter cube. Let me write it down as watt by meter cube, we know it's volume. So if I put watt by meter cube, dV is again volume, so meter cube is cancelled, this will also remain as watt. Similarly, you can also check this, you will get the unit as watt. So this is watt, this is also watt, this is also watt. So basically we are going to talk it in terms of power. Okay, so that's it for Poynting vector. Just practice it, and then I think I'm sure you'll be able to write it in exam.